video, I'd like to go through an example or two of drawing amino acids in the right conformation to have them link into a peptide. And I'm going to do a couple of examples. I'm going to do light, and I'm going to do dark. So L is the one-letter code for leucine. LEU is the three-letter code. And leucine has a isobutyl group as its R group. I is isoleucyl, which is ILE. And isoleucine has a sec-butyl as its R group. Which means that the point of attachment is here on the secondary carbon of what would be a normal kind of egg-butyl group. This introduces a new chiral center in addition to the chiral center for the alpha amino acid, and that chiral center is also S, just as the amino acid chiral center at the alpha carbon is S. G is glycine, GLY, and that has no side chain, it's just a CH2. So that's the simplest achiral amino acid with two hydrogens and no R group. H is histidine, which is HIS. And histidine's R group, its side chain, is a CH2 attached to an imidazole ring. Which looks like that. If you're having trouble remembering where it's attached to the imidazole ring, and you want to remember that it's attached adjacent to the NH, and it's attached in the position immediately adjacent to the NH, but not between the nitrogens, that should make sense because we already know from electrophilic aromatic substitution that if you were to take pyrrole, which only has one, which only has one nitrogen in it. Pyrrole looks a lot like imidazole, except imidazole now has a second nitrogen, and pyrrole undergoes electrophilic aromatic substitution reactions preferentially here at C2, so that there can be more resonance structures possible for the argument material. So if I put an electrophile here, I can write two additional resonance structures for that delocalize the charge onto the carbon adjacent to the nitrogen, and then delocalize the charge onto the nitrogen itself. So for the same reason that pyrrole likes to be attacked at C2 adjacent to the NH, imidazole also likes to be attached at C2. This position is also adjacent to the NH, but it's got the electronegative electron withdrawing nitrogen by induction. So inductively, this position is deactivated relative to that one. So you can remember the point of attachment for your histidine on the imidazole ring by remembering the most likely site for electrophilic aromatic substitution on the imidazole ring. And it's always adjacent to the NH because this lone pair here is part of the pi system and they can therefore delocalize the charge. So there's histidine. This is the basic nitrogen. If histidine gets protonated, right, if it reacts with H+, it reacts at that nitrogen because that's a resonance stabilized ion. If you attacked at this nitrogen, you would introduce an sp3 center there, and there would be no way to stabilize that by resonance. So here we have that, and then we can put this pair of electrons in and delocalize the charge onto the other nitrogen. And that is a general truth that when you are protonating one of these heterocycles, you're always going to protonate it on the lone pair that's in an sp2 orbital, not on the lone pair that's part of the pi system. So you've got two equivalent resonance structures where the positive charge is on the nitrogen that's furthest from the branch and delocalized onto the nitrogen that's closest to the branch. So the basic nitrogen is the sp2 hybridized lone pair, but the position of attack is adjacent to the nitrogen that has that pair of electrons as part of the pi system. And finally, T is threonine, which is THR. And the R group for threonine is one of the 4 amino acids that doesn't have a CH2 group attached. Right? This one being one of them has a CH and a CH3. Threonine has an OH group. And a CH3. So it has a chiral center. And the chiral center for threonine is actually the R chiral center, so it's the opposite in that additional chiral center. Still S at the alpha carbon, but R in the additional chiral center where you have that hydroxy group. So in 3-letter code, this would be leu-ile-gly-his-thr. 1-letter code, it's L-I-G-H-T. So let's draw that peptide. And let's draw it in its completely protonated form, so that the side chain of the histidine will be protonated, and the C-terminus of the threonine will be protonated, as well as the NH3 group on the far left. Always start by drawing the N-terminus on the left-hand side. So we're going to start with a H3N plus. We can then choose to go up or go down. It really doesn't matter. If you're going up, your side chain will be coming out of the board. And in this case, that side chain is an isobutyl group. Right? And your hydrogen will be going back, which will give you an S stereocenter at the alpha carbon. It's always an S stereocenter except for cysteine. It has the same absolute configuration with cysteine, but cysteine is the only amino acid where the side chain outranks the carbonyl group. In this case, nitrogen is priority 1, the carbon that's attached to oxygen is priority 2, the carbon that's not attached to anything except other carbons is priority 3, and hydrogen is 4. So you'll see that you've got that counterclockwise movement from priority 1 to 2 to 3 as you're looking down the CH bond. The next one is pointing down, and when you have it pointing down, the hydrogen needs to come out the board, and the side chain is going to go back, and the isoleucine side chain is a secondary butyl group. So attached to here, we're going to have a methyl group, a hydrogen, CH2CH3, and ethyl group. We need that to be the S stereocenter. We already know this one's the S stereocenter. That's also the S stereocenter. The carbon here that's attached to nitrogen is number 1. The ethyl group is number 2. The methyl group is number 3. And the hydrogen is number 4. We're going to need the stereocenter to look like that. As we look this way down the hydrogen, we're going from the top priority carbon to the ethyl to the methyl. That would be a counterclockwise rotation. It looks clockwise, right? Carbon attached to nitrogen, ethyl, methyl, right? It looks clockwise, but that's because we're looking the wrong way down the hydrogen bond. So there's the isoleucine side chain. Glycine is easy. It's just a CH2. So so we don't even need to draw anything on there. So now we've got our next peptide. Now we're coming down. And we have our histidine here, CH2, and then attached to our 5-membered ring with a nitrogen. And that is protonated. pKa of this hydrogen, 6.1. So at physiological pH, that would actually be neutral, because that pKa is below the 7.4 that's physiological pH. And then finally we have threonine. We've got our nitrogen. We're going to have the carboxy terminus, and we are going to have our hydrogen going back. We've got another chiral center here. We put our OH group off like that. CH3 will be up. Hydrogen will be back. Top priority is the oxygen. Second priority is carbon attached to nitrogen. Third priority is the methyl. Hydrogen is number 4, and that would be the R stereocenter. So we have the S stereocenter at all of the alpha carbons, which means I actually need to be putting this one back. Hydrogen out. We have the additional S stereocenter in isoleucine, and we have an R stereocenter for threonine. There are acidic functional groups here at the N terminus, an acidic functional group here at the protonated imidazole ring, and then an acidic functional group here at the carboxylic acid. The pKa of this is about 15, right? It's a standard alcohol. And so that one is never deprotonated. So now we need to look up in our table, page 1193 and 1194, and find out what the pKa of an N-terminus of leucine is. And the N-terminus of leucine is listed as a pKa of 9.6. And we also need to look up and find out what the C-terminus of threonine is. It'll be in the order of 2, and it's 2.1. So with everything protonated, the C-terminus, the N-terminus, and the side chain of histidine, and light is an easy one to do because 4 of the 5 amino acids in that peptide don't have side chains that are capable of undergoing proton transfer reactions. We have a total net +2 charge. And then we will start taking protons away. The first one we will take off is this one. So if we go from the +2 species to the +1 species by losing a hydrogen, the Ka for that reaction as written is 1.0 times 10 to the minus 2.1. If we then go from the +1 species to the neutral species by losing a second hydrogen, that would be the histidine side chain. That's the next one off. So Ka2 in this case is 1.0 times 10 to the minus 6.1. And then if we go from the 0 to the -1 plus the hydrogen ion, Ka3 is equal to 1.0 times 10 to the minus 9.6. For the third hydrogen, which would come off, is that one. If we take all 3 hydrogens off, net neutral at the N-terminus and the side chain of imidazole, and net -1 at the C-terminus. From the perspective of calculating an isoelectric point, these are the 2 reactions we need to worry about. Those are the ones that both involve the neutral species. The definition of the isoelectric point is the pH at which the peptide is net electrically neutral. Right? It won't all be neutral, but there will be an equal concentration of the +1 and the -1 species. So if we're going to calculate the isoelectric point, those are the 2 pKa's we're worried about. pKa2, which is 6.1, and pKa 3, which is 9.6. What we're going to do is add those two reactions together and get the +1 species in equilibrium with the -1 species at 2 hydrogen ions. And we can write the equilibrium constant for that reaction as the concentration of the -1 species times the concentration of the hydrogen ion squared divided by the concentration of the +1 species. But by definition at the isoelectric point, the concentration of the +1 species is equal to the concentration of the -1 species because the system has to be net electrically neutral. At the isoelectric point. Spell isoelectric correctly. So we can cancel those out. The equilibrium constant is then simply equal to the square of the hydrogen ion concentration. But we also know that the equilibrium constant for this reaction, if we add those two reactions, KEQ is equal to Ka2 times Ka3, which in this case means that the hydrogen ion concentration squared is equal to 1.0 times 10 to the minus 6.1 times 1.0 times 10 to the minus 9.6. That's equal to 1.0 times 10 to the minus 6.1 plus minus 9.6, or 10 to the minus 15.7. And then we're going to take the square root of both sides. Hydrogen ion concentration is then equal to 1.0 times 10 to the minus 15.7. Take it to the 1/2 power, square root. And if we multiply minus 15.7 by 1/2, or divide minus 15.7 by 2, our hydrogen ion concentration